All right, ladies and gentlemen, let's double check our. There we go. So let's double check to see what's going on. I'm going to go to the iPad really quick. Am I at the iPad? Yeah, I am. Yesterday we started to introduce you guys on the idea of a parametric equation, right? And how we introduce a parameter t, and that creates new equations for us. So I'm going to do something here. Let's go to 262. We're going to go to our statistics online transition. And I thought I downloaded this in the iPad. So I'm going to put this here. I'm going to create a note here in Notability. Because what we want to start to look at is the calculus of parametric equations and, perform calculus because this is a calculus course. So, okay, so if I go back to the browser here, so I can put that for all of you who may be at home. We're going to go not to 227. We're going to go to 262. Statistics online transition. Calculus of parametric equations over here. And let's go back now. Let's go take a look at where we're at here. So good morning to you guys at home. Here's a link for you guys, Calculus of Parametric Equations. We're now going to try to dive into that and derive some formulas for you guys here. Okay? So, all right, let's start with some calculus. Now that we know what a parametric equation is, right, your definition goes back up here. And here we go. All right. There's your definition. So remember here, this is an arbitrary curve generally given to us, we already know as, for example, y equals f of x. And we're going to define this a couple of ways. Here's my x coordinate right here. Here's my y coordinate over here. And your point is right over there. So you got your x coordinate, you got your y coordinate, t is in an interval. Now remember, what is this line from Calculus 1? You guys should know what this is. What's this line called? Yes, thank you. Tangent line. You guys remember altangent. And altangent is related to, again, the derivative, right? And derivatives have applications. But this is kind of where you start. What's the tangent line to the curve at a point? Okay, so it's like doing Calculus 1 all over again, but this time with parametric curves. And that's kind of the idea. All right. But remember, we cannot use y equals f of x anymore, although that's there. We're using, and I apologize, it's a notation thing. It really frustrates me. You see how we have x equals f of t? That's just saying function. It's not the same f. So this f here is not the same as this f here. So I apologize. It can be confusing. It used to drive me crazy as a student. I hated that. Okay, so I want you guys to just know that it's just an expression. Y is a function of x. Here, x is a function, another function. It's a different function. X is a function of t. Y is g of t. That's a function of t as well, just notation-wise. But I just want to, warn you guys. Here's the point. So there we go. We're still going to find dy dx, though. Okay? Now, I want you guys to know what's going on here. In dy dx, this is dy dx. This is the derivative. This is y prime, right? Dy dx. The definition is d, well, isn't that y, ladies and gentlemen? That's y. It's derivative with respect to what? X, with respect to x. So now, what are you going to end up with? This is going to be by chain rule, ladies and gentlemen. By chain rule, you're going to have to take, since this thing is y, okay? It's really what you see here. Chain rule goes over here. That's dy dt times dt dx. This is g prime times dt dx, though. Okay? So I want you guys to know that dy, I don't know, maybe use pink here, right? G prime t, this is dy dt, and then times dt dx. That's chain rule. Now, this is a product, but we write this as a quotient here. It's dy dt, right up here as the numerator, divided by dx dt. So the formula for the derivative now is what you guys see here. That if you want dy dx, you want dy dt over dx dt. And that's going to be now, what is dy dt? You really think of that as g prime t over that f prime t. That's what's going on. And of course, the denominator can never be 0. dx dt can't be 0. So it's a very simple thing to get a derivative of a function here. It's just chain rule. Okay? So what I have here now, when I write it down, okay, let's write it down this way. dy dx is dy dt over dx dt. The denominator is not 0. Okay. So let's give you guys a quick example here, because once you have that formula, I could go through all the formulas, but I think I'd rather not. Let's try to find a good example. Okay, let me do this. Let me get an example here. Okay. Say they give you x equals e square root of t, and y equals t minus natural log of t squared. Okay? So I'm going to keep it simple. I'm going to say this. Determine dy dx. So remember, how do you use this definition? Okay, let me say this. Let's color this I don't know, orange, and color this green. Okay? What's dy dx? Take the derivative of what? What function in the numerator? Take the derivative of, what is y? T minus natural log of t squared. And then what's the derivative down here of x? E square root of t. Okay, you guys okay with that? You're using the definition there. That's how you find dy dx. It's dy dt over dx dt. So now you say, well, what's that? Well, you're going to have to do some derivatives here. That's 1 minus 1 over t squared times the derivative with respect to t of t squared. So notice you got chain rule here, ladies and gentlemen. And then this is e to the t by chain rule. This is chain rule for both. So this portion is 2t. This is 1 over 2 square root of t. So remember I said to you guys, derivatives don't go away. You have to still do them. You still have to do chain rule. And so now you get what? 1 minus 1 over t squared times 2t. Everything over the following. E square root of t times 1 over 2 square root of t. Okay, so now a little bit of algebra. You get 1 minus, looks like it'll be 2 over t divided by e square root of t over 2 square root of t. So you might say, what do I do? You got to do some algebra, right? That reminds me of that statement yesterday. Imagine going into calculus 1 with only geometry. Oh, this is actually calculus 2, so it doesn't apply. Ah, okay. But you do need a little algebra, don't you think? You guys know what I'm saying? Isn't this going to be what? T minus 2 over t now divided by e square root of t over 2 square root of t. T minus 2 over t times 2 square root of t over e square root of t. And so, do you guys remember, how do you simplify, right? This is t to the 1. Do you guys know what this becomes? This is t minus 2. Then you get square root of t, e square root of t. This is my dy dx. So there you go. There is, ladies and gentlemen, example 1. And I want you guys to notice something very interesting here. Okay? This is calculus of parametric equations. This is dy dx. I'm going to write it down this way again. It's just function notation. That's a different f. That's not f. What am I saying? That when you find that derivative, isn't this a function of x? I'm sorry, a function of t. So you might look at that and you go, oh, Mr. Judge, dy dx is a function of t? Yes, because x was defined in terms of t and y was defined in terms of t. So your derivative is defined in terms of t as well. And that's a different f, though. Don't think it's the same f. And so that's your derivative function. All right, now here's what's going to come our way. They're going to say note. They're going to say note this. They might ask you the following. What is dy dx when t equals 1? Yeah, that's all it is. Remember, parametric equations are defined. Remember, a point, like for example this, right? Go back to these equations here, right? If t is 1 here, what are they really talking about? You know what they're saying if t is 1? What they're saying is x, then the x coordinate is e square root of 1, which is just e. That's your x coordinate. What they're saying is y is going to be now, plug in 1 for t, 1 minus natural log 1 squared. But you guys know that's equal to 1. So when t is 1, the point on the curve is e comma 1 here. That's what I want you guys to know what's happening here from parametric equations. That's your x, y value. That's your point on your curve. Hmm? T could never be -1. Why can't T be -1? That's a good question. Why can't your T be -1? Oh, is it? Oh, Y is -1. No, because you know why? Oh, no. You know why? Natural log of 1 squared is natural log of 1, which is 0. So you have 1 minus 0. And then 1 minus 0 is just 1. E to the square root of 1 is really, so you plug in the 1 there is what I'm saying for T. I'm trying to get something up here. Let's get our code. Yeah, T has to be. Notice the following, though, just so you guys know, because I'm about to show you guys something here. Okay, because of that domain, it's two things here about T, so you guys know. T is a restricted domain there. They didn't tell you what T has to be, but remember this, is T has to be greater than 0, okay? Not greater than or equal. You go, how come not equal? Well, I think it can be equal, sorry. No, it can't be. You guys know why it can't be equal? Natural log, right? Could you have natural log of 0 squared, which is natural log of 0? No, undefined. So in other words, T is strictly bigger than 1. And I'm looking up something here as I'm multitasking. Okay. So to kind of go back and remark here about this parameter value of T being 1, they want to know what's the derivative of that function when T is 1, right? We know at the point what that point is. What they're saying is simply let T be 1, which means you have really what? T minus 2 over square root of T, e to the square root of T, T being 1. 1 minus 2, square root of 1, e to the square root of 1, which is negative 1 over e. So you can actually find, ladies and gentlemen, the derivative at a point on the curve. You say, how do I find that coordinate? Well, you find the coordinate, T is 1, the location is E1. We just looked at that. Okay, so I know the derivative at the location E1. So if I go over to Desmos, here's the thing about Desmos, right? Let's get rid of all of this stuff. Desmos graphs parametric equations. What was your x coordinate? Do you guys remember the x coordinate? Wasn't it e to the square root of t? E square root of t. Let's find our t. Okay. Comma. Oops. Comma. What was the other function? What was the y function? Okay. T. Let's try that out. Minus. I'm going to look for the natural log function. What's that? Natural log of what? T what? Squared. Now T can't be 0. Something's odd there, but whatever. Let's say 500. Okay. Oh, that's kind of weird. What just happened there? Did I finally break Desmos? What happened in Desmos here? Something's weird. Anyway, what happened in Desmos? Desmos, you're broken. Huh? Yeah, I don't know. What do we do with that? How do you close the tab? How do you where do you mean close the tab? Hmm. Oh, geez. Okay. Let's see if we can do that. Okay. E, exponential function. Okay. Well, let me find that. Do you use Desmos? No. You just use iPad. Good for you. You know what kind of happens is you get old and everything doesn't make sense with technology. Is that none of this makes sense to me, by the way? E, square root of t, comma, where's t? T squared. And what does it mean? Maybe it doesn't like my. Who knows? Maybe what does it not like? Let's find out. Where's your e? I'll do it this way. E raised to the t, square root of t. And okay, we got 0 to 1, but let me change that 0 to, say, 20 at least or something. Okay, well, maybe that's a little better, right? And you guys already know by now, I do not like my curves ever to be what? Red. Because I use red for something else. But what I want to say to you guys, take a look at this, okay? This is the curve. That's your parametric curve. If I were to plot the point when t is 1, okay, remember the coordinates. That was E1, right? E, comma 1. Label it. So if you look closer, what do I know? At that location, E1, that happens when t is 1. At that location, I have a tangent being negative 1 over e, right? So this is that tangent we're talking about. So you might say, what does that really mean again? Let's note. What they can say to you is this. What is the equation of the line? Remember that from Calculus 1? Tangent to the curve. When t equals 1. They're trying to find that equation of the line tangent to the curve at this location. You remember, this is the what? X coordinate. This is the y coordinate. Okay? Do you guys remember what you did from algebra? Do you guys remember that? What do you guys do? This very famous question. Y minus y1 m tangent x minus x1. That's all from Calculus 1. You guys are actually done with all the information. How come I say you're done? The point is E1. This happens when t is 1. This is that one and only point you have. So this number is 1, and this number is E. What is M tangent? You found that already. M tangent's what? Negative 1 over E. y minus 1 becomes negative 1 over e x minus e. Okay, that's a Calculus 1 question. Is that true? Do you guys see what I'm saying? So if you do a little bit of algebra, you now get y minus 1 becomes negative 1 over ex plus 1. Is that true? And then I can add 1 to both sides, and you get altangent, which is what we're looking for. So this is the equation of the line tangent to the curve at the location. This is also known as al what? Tangent. So you might say, oh, is that true? Let's go to Desmos. Let me double check. Maybe I made a mistake. You guys remember how this all worked? Y equals negative 1 over what? E. X. Was that minus 2 or plus 2? Plus 2. And then you guys remember, I'm going to put that color red. I like that standing out. Now, something bothers me. Did we make a mistake on this? Something's bothering me. Let's go back and look at the notes. Did I screw that up? It might be. I'm going to check my notes. Oh, was there a 2 somewhere? Oh, I think there is a. Here it is. Is that 2? I think there's a 2 there, right? And so when t is 1, that's negative 2 over e. Thank you. Okay. And so that's negative 2 over e. Okay, so we get a 2. And so negative 2, I think this will be plus 2 now, right? So that ends up being plus 3 then. Let's double check if that looks right. Let's double check. Negative 2 over ex plus 3. Ah, beautiful. It looks beautiful. That's what we're looking at. You guys remember? That's altangent. So you guys can see essentially how what works. This formula just for that first derivative. That first derivative formula works. Anyway, those are all classic kind of questions, you know. Okay, so let's give you guys another example so you guys can kind of look at this here. Oh, we're back. No, not Desmos. Let's look at another kind of example here. Oops. Come on. Where are you? All right. I'm going to say now what? X is cosine theta. Go theta. Cosine theta plus sine 2 theta. And then y is going to be what? Sine theta plus cosine 2 theta. Theta now is 0. So they want you to determine dy dx when theta equals 0. Now you might say, Mr. Judge, where's my t? Well, sometimes they give you t, sometimes they'll give you theta. So don't get discouraged. Okay, so yes, if you rather say, I rather get use of t because you just showed me one example. All right, then do it as t. Okay, so then you say dy dx, remember the definition is dy dt or d theta over dx dt or d theta. So sometimes it just uses a different parameter letter. And you might say, why did they choose theta? Because it was a trig function, but it doesn't matter. So what is dy dt? Do you guys know? Take the derivative of y now. Isn't that derivative of sine is what? Cosine. Now, what's the derivative of cosine 2t? Well, you're going to use chain rule. So the derivative of cosine, isn't that minus sine? Minus sine 2t times what number? 2. And what's dx dt? Derivative of cosine is minus sine t. And then chain rule again. Derivative of sine is cosine plus cosine 2t. Don't forget by chain rule, that's times 2. So you're taking the derivative of these functions here. And then they now want to find t, or let t be what number? T is 0. So if t is 0, okay. What's cosine 0? Do you guys know? 1. Good. So isn't that 1 minus 2 times sine is 0, really? 0? Negative 0 plus 2 times cosine of 0 is 1. So here we go. 1 over what? 2. Okay. Is it negative? No. It's positive. Yeah, 1/2 here. Okay. So that's the derivative of that function when t is 0. And then what's the equation of the line tangent to the curve? When t is 0. Very common. So what do you think you're going to do with t now? Let's see, what's your x coordinate when t is 0, right? X will equal, cosine of 0 is 1, and then sine is 0, because 2 times 0 is 0. Sine of 0 is 0. So x is 1, and then what will y be? Sine of 0 is 0, plus cosine of 0 is 1, so it's 1, 1. Is that right? Did you guys see my point? Those are your x and y values. Just plug in t being 0. So they're really saying the point is 1, 1. Yep. Double check. Plug in t as 0 into the original parametric equations. Plug that in. Now, you go, well, what does that do? Well, y minus y1 is m tangent x minus x1. Yeah. Well, what is sine 0? 0. Plus cosine of 2 times 0. 2 times 0 is 0. What's cosine 0? 1. So 0 plus 1 will be 1. So x is 1. Y is 1. M tangent is 1/2 y minus 1, 1/2 x minus 1. So, ladies and gentlemen, now add 1. What does y give you? What's 1 minus 1/2? Isn't that 1/2? Al what? That's Al tangent. Now, again, you might say, well, how do I believe you? Well, cosine t, so let's go back. X is cosine t. This is the x coordinate first. Okay? So, parametric. Cosine, use the function. Cosine, okay. Come on, cosine. Cosine t. Was that plus or minus? Plus sine 2t, right? Now just come out of there and put a comma. So here's your comma. Now I think the other one is sine t, right? So sine t was that minus? Plus what? Cosine 2t. Okay, now remember we said this next point is at 1, 1. That happens when t is 0, by the way. So, this curve that you guys are looking at, by the way, this is a parametric curve. It's a relation in the xy plane. Can we find that? What was the equation of the line tangent to the curve? Y, wasn't that 1/2 x or something? And then sure enough, ladies and gentlemen, doesn't it look like, again, your tangent line to the curve at that point, at the point t is, when t is 0. So as you guys can see, that makes a lot of sense. Does that make some sense? You're still in the Cartesian coordinate system, x, y. Okay, so, okay. Give you another example. What else did you guys do from Calculus 1? Do you guys remember this? From Calculus 1, they could give you x equals e to the t, y equals t minus 1 squared. Okay? I don't think they gave you a limit on t, but whatever. I'm going to say here, for what t now is well, for what values of t is the curve c increasing? Okay? Now, I just want you guys to note something here. You say, what do you mean the curve? Well, if they say y is f of x, that's a different f. They're really asking where dy dx is what? Positive. But it's in terms of your parameter value now. It's not an interval of x. It's a parameter t. Where's the function increasing? The function is represented by the curve. So you might want to say, okay, then don't we have to find the what? The derivative? And you do, because that derivative, right? What is dy dx? Is what? Dy dt over dx dt. So what's the derivative of y? Isn't that 2t minus 1? If you take the derivative of the y function, right? And what's the derivative of the x function? Isn't that just e to the t? All right, now let's go back here. I want you guys to know something here. Go back to your function here, right? You're trying to do sign analysis. Is that true? We're doing sign analysis on this derivative. And was there any restrictions on t? T could be any real number, is that right? The domain, right? T is any real number. There's no restriction on t. So in that case, then you go, what about my sign analysis? Well, remember what do you do? You say 2t, well, 2t what? 2t minus 1 equals what? 0. You find where the numerator is 0, and you find where that denominator equals 0. This is going to be t equals what? 1. Okay? And over here, what do you say about e to the t being 0? It never happens, right? E to the t is never 0. So then you might say, well, what does this analysis tell me? What this analysis says to me is that we only have to check 2 regions. This is in terms of t now. These are t values. When t is 1, that derivative, call it y prime, equals what? Equals 0. Okay? The derivative is 0 when t is 1. So we have a horizontal tangent when t is 1. Now, do your test points. -1 is a test point. +2 is a test point because what do you have? You got 2 regions here. So go back to the curve here. No, go back to your derivative, right? So you're going to test this derivative. When t is -1 as a test point, plug in -1 for t. The denominator is going to be positive because e to the -1 is 1 over e. So that's a positive number. So you really only care about the numerator. So -1 for t, -1, is that -2? 2 times -2. So here's my point. Region 1 is negative. Plug in the test point of 2. This is what I mean. Right here. T is 2 now. The denominator, e squared, is positive. But the numerator is also positive because 2 minus 1 is 1, and 2 times 1 is 2. So here's what you do here. We found sign analysis on that first derivative. But it's all in terms of your parameter value, t now. So when they say, for what value of t is that derivative increasing or the curve increasing? Well, it's going to be when t is greater than 1. So you have an increasing function when what? Time value is bigger than 1. You also know you have a decreasing function. Is that true? When t is what? Less than 1. Why? You guys remember this? That's a negative, slope, positive. This is about the first derivative. This is sign analysis on the first derivative. That always gives you increasing, decreasing, even if it's parametric, but it's now in terms of t. Now, you can always very easily find the x values. You go, what do you mean? How do you find the x values? Well, you know, when t is 1, what's going on, right? What happens when t is 1 here? What is x? So when t is 1, x is e. That's e to the 1, right? And what is y? Well, that's 1 minus 1 squared, which is 0. So this happens when x is e. So I might even say to you guys here, I want you to note something here. And t is 1, what do you guys have? E's at that location, e 0. So I want you guys to note this too. When that derivative equals 0, y prime equals 0 happens when t is 1, and it's at the point e 0, right? You have a horizontal tangent, right? So you have a horizontal tangent. So what is our curve? E to the t and then t minus 1 squared. Okay. Let's look at Desmos. And what was the other one? T minus 1 squared? Mm-hmm. And t could be anything. So I'm going to put negative 20 to positive 20. T is any real number. And then the location now, the point we looked at now, by the way, wasn't that E0, I think? Yeah. What's a horizontal tangent? Isn't that a horizontal line? So what do you guys think? Is that curve decreasing from negative infinity up to e and then increasing from e to infinity? Do you guys remember calculus 1? Look at the curve. This is the curve. The function is decreasing from oh, wait a minute. Oh, whatever that is. We're gonna look at some details there. Your function's decreasing and then increasing. So what happened there? Ah, I know what happened. Let's take a look. Okay? Let's take a look at this. What curve is this? Is that right? So what does that mean? Y is what? Natural log x minus 1 what squared? Just so you guys know. So that's the curve they're talking about, by the way. Now, what's the domain of this curve? X is going to be what here? X has to be greater than 0, right? Because you can't define that. So anyway, I just want you guys to know that. And that makes sense here because e to the t is always positive, no matter what t is. So okay, I can see that now. So this curve, as you guys did the analysis, for the t value being greater than 1 or t value being smaller than 1, yes, the location here is E, that point. So, I mean, we could even talk about, horizontal tangent at E. And so now that curve information makes a lot of sense when you go back and look at Desmos. You go, oh, okay, that makes some sense. But anyway, so they're asking you this in terms of, t though. But anyway, I want to kind of put that all together for you guys so you guys can see that curve. Now, that brings me up to the next point. What about concavity, right? If they say, what about concavity? Yeah, so what about y double prime? Okay, second derivative. What's the definition? Do you guys know? This is the definition of the second derivative. It is the derivative of the first derivative. Remember, this is y prime. So you do have a way, if I go back to Parametric and the notes, I gave you the classic definition, or I showed you guys how you deduce the formula for the second derivative. Okay? Here's the formula. D squared y dx squared equals d dx dy dx, which is what I just put down, definition. But I want to make sure you guys understand. You see this dy dx? I replace it with u of t. Now, the reason I did that in these notes, I'm just trying to say that's a function of t. So I had to find another letter. I was just trying to make sure people were clear. Because remember, when you had dy dx, wasn't that a function of t that we said? I used f of t, but I can use any letter. So bear with me. So I just replaced that with the u of t. Now you say, how do they come over here? Do you guys know? What is this? Chain rule. Chain rule for derivatives. So dx of a function of t is du dt times dt dx. This is all by chain rule. So I wrote chain rule as a quotient now, meaning du dt is right here, and then, that dx dt. Some funny stuff there. Now, you might say, what in the world do you have here, right? Du dt, by definition, this is, well, what was u again? Here's what I'm saying what u is. Let me get a red. This is u right in here. This is u. Okay, so du dt is d dt of u, where u is that dy dx. The denominator is just still dx dt. So in your book, you say, why did they do this here for the second derivative? I'm just proved it to you guys. This is where it came from. This is the logic. The point is, in order for you to get the second derivative, this is the formula you use. Yes, you have dx dt, but what you have to do is you have to take the derivative with respect to that first derivative. You take d dt of that first derivative. And then that'll be over dx dt. This is your proof. It's a proof that's in your book, and it's a proof I just went through. So, you know, you might say, well, how am I going to do that? Well, let me go back and let me see if I can do something here. Let's make it kind of simple. Let's go over here. See, where's the first derivative? Yeah, we're going to use this one here, okay? I'm going to try it out here. X equals e to the t over, okay. So for that example that we had, maybe I should copy it. Just to be complete. Give that to you. And then what do you know? To use that formula, we know what? We need to know dy dx. And we got it. Okay? So, the second derivative formula. I need d dt of the first derivative divided by my dx dt. Double check, ladies and gentlemen. This is what I'm sharing with you guys when I did the derivative there. Okay, you guys with me on that? Second derivative. It's y double prime by definition. So I need my d dt numerator with respect to the first derivative, but I have to divide by dx dt. That's the proof I gave you guys right here. This is the proof. So, all right. So you say, oh, what does that mean? Well, I have to take d dt 2 t minus 1 over e to the t over dx dt. And that was that first derivative I'm saying here for you guys. Okay, do you guys know what dx dt is, by the way? Yeah, it's e to the t. Is that true? Dx dt? So I'm going to do the easy one first, right here. That's dx dt. But now I have to take the derivative. This is, what do you guys use here? Anybody know what you guys use for the top? Right? How do I differentiate with respect to t a quotient? Quotient rule. Okay, you gotta use quotient rule. E to the t squared, e to the t times the derivative of the numerator, 2 t minus 1 minus 2 t minus 1 e to the t. 2 e to the t. Is that right? You guys okay with that? Double check my work. Double check. Is that what you guys get? That's what I get. And then this becomes 2e to the t minus 2e to the t again, but this time t minus 1 over e to the 2t times e to the t. 2e to the t, I guess I can factor that out. We have 1 minus t minus 1 over e to the 2t times e to the t. Double check if I factored out this okay. Okay? I think I'm good. There it is. There's the term. 1 minus. Okay. And then sure enough, what happens? E to the t goes away. So 2 now. 1 minus t plus 1 over e to the 2t. And so it looks like we get 2 minus t over e to the 2t. Now we have that second derivative. Double check to see if we made a mistake. Oh, did I make a mistake? Hold on. Where? Let me see if I did. Okay, I got 2e to the t minus 2e to the t, t minus 1, 2e to the t, 1 minus t minus 1. So 1 minus t plus 1, 2. Oh, why I don't distribute right here 4 minus t? No, it's fine as an answer. You know, it's factored form and it's okay. And, you know, so here's a second derivative. Now, I want to make sure something kind of makes some sense, though. Yeah. Okay. Let's note something here. Remember we asked the original question about concavity? What's sign analysis on the second derivative? Remember about concavity? So if you want to do sign analysis on that second derivative, set the numerator, because you have a quotient, equal to 0. Set the denominator equal to 0. You guys already know this never happens, right? But here we get 4 minus 2t is 0. We get 2t is 4. We get t equals 2. So for sign analysis again, on the second derivative now, okay, at 2, I get a second derivative equal to 0. So I have a test point to the left on the second derivative, a test point to the right. So I got 2 regions, okay? It's test points, all on the second derivative. So if I plug in 0 on the second derivative, you guys know, isn't that positive? If I plug in 3, I get negative. So what this is saying, these are t values here, okay? These are values of t. The curve is concave up for time values being less than 2, and it says it's concave down for time values being greater than 2. If we did everything okay, not sure we did, but let's double check now. Okay, so we're looking at the second derivative here. Hopefully we did our algebra okay. I hope we did. But if I go back to Desmos now, there's an issue about my t value. You guys know what we're saying? This curve is concave up everywhere. Yeah, you're going to have to go back to the domain, so you guys know. So remember, this is y versus x. There's no t here really. So you're going to have to go back to the domain of the function. So I just want you guys to know that you can do your analysis there, but go back. We're not, sorry. We're in Notability. So you got to go back to this function here. Anyway. It's kind of interesting. Remember, this is for t, though. And yes, t could be all real numbers, but you might do something like this here. See this here? Remember this? Didn't we say the x value is positive, right? And that function is really this. You know, e to the t is positive. Yeah, that's positive for all what? For yeah, you're gonna have to go back to that function there. But anyway, I don't think they're gonna give you that, but whatever. X has to be positive. Okay. Anyway, I wanted to get through. Let's double check here. I wanted to get through the first or second derivative at the very least. So I'm looking at my notes here for you guys. And then you got area under a curve. So we can talk about that. And then you have, you know, how do you find an area under a curve doing an integral? I don't think they give you very many questions like this, by the way. I think it's one or two. But, you know, I could derive that for you guys. Maybe you want to read about that. And then now over here, this is what I want to get out too, arc length. So you can actually deduce arc length, and I'll prove it to you guys next time. This is the proof, though. Yeah, it's a proof. You could read it. It's in your book, but I went through the demonstration and the picture of it. We'll go through it next time. But you can find arc length, and it's using this formula, and we'll go through it next time. And believe it or not, you can actually find surface area. There's a surface area formula, too. Surface area is 2 pi RDS, we know. So you can actually rotate the curve about the x-axis, and you get 2 pi y square root of that arc length. And then you say 2 pi, rotate about the y-axis, 2 pi, and then it's the arc length again. But anyway, just to let you guys know, you can find arc length and surface area for the same kind of things. And we'll go through these things next time. And I'm looking at, sorry, you guys don't know what I'm looking at home. I'm looking at the worksheet I gave you guys. You can find area under a curve. I'll go through it. You can find arc length. I'll go through that. Here's the proof. It's also in your book. And you can actually rotate a curve about the x and y axis to get surface area. Right here. So those formulas that are coming our way. right, let's see. Let's get the audio out here. Let's double check. Okay, it looks like we are good to go here with our audio. Now, remember what we've been working on. We've been working on parametric equations, actually calculus of parametric equations. And I'm going to share with you guys here some more calculus, meaning what do you do when, excuse me, we're talking about area under a curve. Now, remember, this is over an interval AB. Okay. So we're going to take a look at this picture. And remember, these are parametric equations here. Okay. So this is in my worksheet, the notes I sent you guys last time. And demonstrate to you where this comes from. Now, notice I have in red orientation. That's going to be an important thing. The orientation, because your time between alpha and beta, where this is t is alpha, whatever that value is, that corresponds to your x value here being a. So that's not the same letter. That's alpha. Alpha versus a. And then that's your initial point on the curve, to let you guys know. That's IP. And then terminal point, you know, is when your time value, or t, your parameter, is beta. But that corresponds to x being b. So alpha and beta are not the same. And your equations are parametric. Now, I hate to say, remember that y is simply some function of f of x. It is, but that's a different f. So in other words, you go, what about this f and this f? No, they're different f's. It's just saying function of time, function of x. So just because it has the same letter f, don't think it's the same. Okay, that kind of always bothered me. And sometimes when I was a calculus student, even now I'll put h in lecture to give it a different, you know, name, but that's a function, whatever. But notice something about this. Your y value is strictly positive. So this is area under a curve where your function is positive. Okay, that's another way of saying all the y values are positive there. And your orientation is well, your orientation is going that left to right. In fact, I'll just say it's your time value is increasing. T is increasing from alpha to beta, right? So you're looking at this t, alpha to beta. So t is increasing. That's going to be important for us because now, and that's what I'm saying, if t is increasing also, you notice this. You guys also want to notice that your x coordinate value is increasing. So all these points on this curve, okay, even though your time is getting bigger, this is also saying that your x coordinate value is getting bigger. X is increasing. And when x is increasing, getting larger, the corresponding x values here, okay, that means dx dt is positive, just so you guys know. Because x is increasing, and x is a function of time, t, if you want to look at it that way. Okay, so I'm just kind of pointing out some of those details that I'm mentioning here in the notes, that the curve C is above the x-axis, the curve is transversed once as it increases from alpha to beta. This is what we're saying. So my x-coordinate is increasing. That means dx dt is positive. So now I'm gonna really take a look at your area formula. If you guys remember, you got the approximating rectangle, where that's my dx. Remember this approximating rectangle for area under a curve. And, you know, this is the formula for area under a curve. You take your y value, the value of the function, also called f of x, or in this case, h of x. Okay, so you guys remember that. And then you have this thing called dx. But now what we're going to do is remember the y function here is just g of t. So the y coordinate of this y is right here. It's g of t. And then you say, well, what do we do with dx, right? What's happening with this dx value? Maybe we'll color it green. I don't know. Well, what is x anyway? X is over here, right? F of t. So if x is f of t, what that means over here, because it's parameterized, is that dx with respect to t is f prime of t. Let me get rid of this. Come on, let's go to eraser. Let me write it better. That dx dt now is f prime t dt. So that solving for dx gives you what you guys see here. So this is now, whatever color we used. Okay. Dx, this is now f prime t dt, solving for that. And remember, x is going, or my time value now is going from alpha to beta here. Okay, so they say x is a. Yeah, so remember what that is. If x is a, yeah, your x coordinate down here, a value corresponds to the t value being alpha. Okay. All right. So I'm just looking at something here. Okay. Anyway, here's what you have here as your area formula. You know. So I just want to kind of let you know that, and then be careful here, because what happens, if you guys know, what happens now if x is not increasing, meaning you got the following odd situation, right? Where when x is a down here, that's really the terminal point. It's not your initial point. And over here, you have the initial point, and that happens when x is b. It corresponds to t being alpha. This t is always increasing, right? Time is really, we define it that way. Alpha is less or equal to t, less or equal to beta. But the problem is you have this orientation for your curve is going the other way. And remember this, you're approximating rectangle now. That delta x, this is where the real issue is. This delta x is no longer positive. This is negative. So that's kind of what's going on here now. So everything is still the same. So you say, okay, y, and here's my y. And then your dx is still f prime t dt. However, your lower limit now, if x is alpha, that corresponds to the beta value now. And when x is b, that corresponds to the alpha value. So if you want to have it make sense that alpha is less than or equal to t, less than or equal to beta, remember, you can switch your limits, right? Where now this is alpha, this is beta, where you're seeing alpha and beta the way it's supposed to be. But remember, when you switch limits, you have that negative sign. So in other words, you're going to have that situation, you know, if your x coordinate is getting smaller. You say, what do you mean? Yeah, as you plot these points with your t value, all the corresponding x values are getting smaller. So in other words, dx dt is negative because x is decreasing now. So it's only an issue when you're finding that area here, to let you guys know. Anyway, I wanted to point that out. And so you're going to have that area formula. We'll see what kind of examples we have. But the real formula for today, because you'll have a few area questions. They don't even give you very many. They don't give you very many area questions. They give you many arc length questions. So now we're going to go back to the situation again where you have your x coordinate, increasing, which means dx dt is positive because my initial point is on the left, my terminal point is on the right. Alpha is still, your time value is always defined this way, alpha less than t less than beta. Because that's how we define our intervals. We go from smallest to largest. X is still f of t, y is still g of t. We're now going to try to find the length of this curve. Okay, so we're going to try to find that length here. That s. That's what we're looking for. So we're going to recall that the arc length formula is defined in terms of increments, meaning s is that sum of these ds's, right? Remember we talked about the ds's there. This little ds. So that's all we're saying here. And so what that means is, remember this is the arc length formula, right? So this is what we're given. We're given the arc length formula. We already know that already. Okay? All right. So we're going to try to convert the arc length formula in terms of parametric equations now. So you're assuming that dx dt is positive as illustrated. And then we could just switch our parameters now, where your alpha to beta. Okay. But then the real question is, what happens here? Okay? What happens with what we're going to integrate? But the real issue, in all honesty, is what happens right here. Okay? What is dy dx? Well, we seen last time, dy dx is what? dy over dt divided by dx dt, and you're supposed to square that. Take the square root. So now, all I'm going to do here for you guys is use algebra. Okay? To derive the arc length formula. So what is the algebra? Well, essentially, you're going to want to do what here? You guys see that there? We're going to have to try to add two rationals. You're going to replace this 1, really with, you can think of that, replace that 1 with really 1 squared, because 1 squared is 1, and that's why you have what you have here. dx dt over dx dt is really 1. This number right in here. Right? That's really 1. But we're going to do it in such a way where you have the same denominator, dx dt. And so we're going to square both numerators and denominators. And this is over, again, the square. Let me give you guys some algebra, what I'm talking about. Right? A over b squared is a squared over b squared. That's what we're saying. So that's how we went from here to here. But then I took the square root, of the numerator, because I have a square root of a sum with the same denominator. And so we took the square root of both numerator and denominator. And as you guys know, down here, okay, that's the definition of the absolute value of dx dt. And so since dx dt is positive, that leaves you dx dt. And then over here, we can cancel our dx's here. So this is like having 1 over dt. And my numerator I'm not touching. That's just leaving it as dx dt squared plus dy dt squared. And so what you end up with, ladies and gentlemen, just algebraically speaking, is that dt over here, that's alone, divided by that, becomes up here. Because that's 1 over dt. You're dividing a whole number by a fraction, so you're multiplying by the reciprocal. So that's how we got our dt. But then this stays the same as dx dt here. This is what we end up with here under the radical. So this is a very famous arc length formula. And sometimes it is easier to write it as, that's alpha beta, that's your t value. X prime t squared plus the y prime of t squared under your radical, and then that'll be a dt. So this is where the very famous arc length formula comes from here. Okay? And then I go through this derivation here, but it doesn't matter. I don't even think they're going to give you that. It's going to be the same area formula. Okay, so you say, yeah, it's going to be the same area formula here, even when x is decreasing. You know, when you switch the limits here, and that negative sign, dx dt is negative, so minus a minus, you get the exact same arc length. So it doesn't make sure. So in other words, you guys can read this proof I gave you guys, switching the limits and using that negative. It comes out to the same exact arc length formula, and that should make sense. You say, why does that make sense? Why is it the exact same formula, irregardless of your orientation? It doesn't matter what your orientation is. It's not a negative arc length. Because if you switch the orientation, you're still looking at the length of a curve. It's still S. It's the same value, how long that is. So orientation does not matter for arc length, and that's what my proof shows you here. The orientation doesn't matter for arc length. It matters for that area, but not arc length. So orientation does not make a difference when it comes to arc length. And that's my conclusion there for you guys. So you're going to have the same arc length formula. And then, you know, we could go to surface area, but let's try to look at maybe some examples. And you go, okay, where's some examples? Calculus here. So look at some more examples of some of these things here. So I'm going to have to dig through, find some good examples. And we've got to be careful here. All right. Anyway, yeah, let's be careful with some of these examples. What do they want to know? Yeah, let me be careful. I think I'm going to go with your book questions here. Just be careful. Should we try that one? Okay, let's try this example of arc length. So let's determine the arc length. This is a kind of a classic question here. X equals, well, let me double check really quick. Yeah, there's only a few kind of questions they can give you, but anyway, okay. All right. We'll just dive in. I thought I'd try to find a simpler one, but maybe not. This is simple in a sense. Okay, so this is t goes from 0 to pi. So determine the arc length s over 0 to pi, okay? So I'm kind of interested in Desmos here. Let me see if I can do that here, okay? So function, exponential function. You know what I'm going to do? I'm going to use e. Let me see how that looks here for you guys. E to the t. Cosine t. Okay. Come out of there, comma, e We'll do sine t. And then 0 to pi. All right. Okay, guys, see what we're trying to do? We're going to try to find the arc length there of that curve. And again, all of these curves are very specially chosen. So I'm looking in your book. I'm trying to find some, I'm trying to find some good examples. Anyway. Okay, so let's find the arc length. So here's essentially what you guys want to remember here, right? The arc length formula is from 0 now to pi. Those are the two values. Sometimes I just put x prime squared plus y prime squared, all under the radical dt. Very, very simple formula. But like I said, because you're trying to integrate a square root, very specially chosen questions. Don't try to make anything up and try to think you're going to integrate it. You're not going to be able to. But notice what's going on here. When you find your x prime here, right, because that really means dx dt. And then I have to find y prime, which really means dy dt. So that my dx dt really is that derivative of e to the t cosine t. Notice, ladies and gentlemen, your derivatives do not go away. So you're going to try to differentiate this. You say, what is this? Well, product rule. So it's e to the t. What's the derivative of cosine? Is that minus sine? And then e to the t cosine t. So I'm going to write it this way, ladies and gentlemen. I'm going to write it as e to the t cosine t minus sine t. Okay? So this is really my x prime. Now, dy dt, which is your y prime, I differentiate again, but this is e to the t now sine t. Product rule again. We use product rule. So we take out e to the t, derivative of sine is cosine, and then you add, pull out your sine, and you differentiate e to the t. We get e to the t, and notice you get something very similar, and I'm going to write it this way. Cosine t plus what? Sine t. Now, that's what we call y prime. So you want to do this. You're going to get x prime. It's looking for a highlighter. Okay, x prime, that's dx dt. And then you're going to get your y prime. And then that's dy dt. You got to square them and then to take the square root. And then integrate. Not so easy to do, generally speaking. But these are specially chosen. So you say, am I supposed to square this? Yes, you square this. You square this. Now, let me share with you guys some algebra. X prime squared becomes e to the 2t now, cosine t minus sine t. We're going to square that. You're squaring both. You're distributing that power of 2, right? You're using some algebra. Same thing for this y prime squared. We'll get e to the 2t now, but this time you get cosine of t plus sine t squared. So you're going to distribute your power of 2 there. You're going to do some algebra. Now, don't forget, you're taking the square root of x prime squared plus y prime squared. And then now that's going to be the square root of e to the 2t cosine t minus sine t squared plus e to the 2t cosine t plus sine t squared. Take that square root. So don't forget, ladies and gentlemen, here you get to pull out your what? You get to, I should say this, factor e to the t. So when you do that, you're going to get cosine t minus sine t squared. Let me put parentheses here. Let's do this. Let's do it the right way. Okay? Factor that out, and you're going to get cosine t plus your sine t squared with the bracket. Okay? And that's under a radical. So you're going to take the square root of e to the 2t. So you're going to take the square root of a product. Square root of product of square roots. And then that's going to be that whole cosine t minus sine t. You're going to square that. Plus cosine t plus what? Sine t squared this. And it's all under a radical. This is e to the t. And I'm just going to copy this. Come on. Paste it. So we're going to have to use, I would say, right in here and right in here. You have to use FOIL. Square this. Square that. And when you use FOIL in here, right, you're going to get e to the t square root of cosine squared t minus 2 cosine t sine t plus sine squared t. Okay? Then FOIL the second one. And when you FOIL the second one, it's all under the radical. It's cosine squared t plus 2 cosine t sine t plus sine squared t. And I'm going to do it this way because I don't have a lot of space. So I'm going to kind of communicate it all that way. Okay. Now, what do you guys notice about the middle terms here? Don't they cancel? These two middle terms? And then you say, what is cosine squared plus sine squared? Isn't that 1? And then what's this other cosine squared plus sine squared? Isn't that 1? So, ladies and gentlemen, what you have is 1 plus 1 under the radical, which is 2. Or we say this is the square root of 2 e to the t. That is what you have to integrate, okay? That is what's under here, this radical here. We just computed this whole thing, okay? And so your surface area here, I'm sorry, not surface area, arc length is that integral from 0 to pi now, the square root of 2 e to the t dt. So you get to now factor out that square root of 2, 0 to pi, e to the t dt. It's arc length. So the arc length becomes square root of 2, e to the t, 0 to pi, square root of 2, e to the pi minus square root of 2, e to the 0. So your final answer will be square root of 2, e to the pi minus 1. So here is our first arc length question, ladies and gentlemen. It's your first arc length question. Okay, you guys okay with that one? I'm just looking at the book here, seeing if I get some interesting kind of questions here. Okay. So here's how you handle an arc length question. Let me see if I can get another one here. Let's try another one here for you guys here. Another arc length question, for example, here. Let's say they give you x equals 1 plus 3t squared. And then y equals 4 plus 2t cubed. And then t is from 0 to 1. Okay, let me double check here. 1 plus 3t squared, 4 plus 2t cubed. All right. Let me see in decimals now, because I kind of want to show you guys in decimals. Kind of like that. Put a parentheses here. So 1 plus 3t squared, comma, 4 now, plus 2t cubed. And then that t goes from 0 to 1. All right, that's kind of a simple, nice curve to look at in terms of parametric equations. We're going to try to see what that arc length is. We'll get rid of that label. Okay, so remember what you want. You want to integrate here from 0 to 1. This is your t value. The square root of x prime squared plus y prime squared. This is dt. Arc length questions. Okay, we need x prime. You say, well, what is x prime? What is that? That's dx dt, which we have to differentiate 1 plus 3t squared, which we know is 6t. Is that right? And then y prime is dy dt, which would be d dt, 4 plus 2t cubed, which is 6t squared. Okay. So x prime squared plus y prime squared is 6t squared plus 6t squared squared, which gives you 36t squared plus 36t to the 4th. Okay, in terms of some algebra there. So don't forget to take the what? Square root, okay? So that your arc length will be from 0 to 1, square root 36t squared plus 36t to the 4th with your dt. Now you say, how am I going to integrate something like this? Use here, ladies and gentlemen, you're going to use some algebra here. Okay? You say, what do you mean? I can factor out 36t squared, and I'm left with 1 plus t squared. Square root of a product is product of square roots. So this is going to be 6t square root of 1 plus t squared. Okay? So your arc length will be 0 to 1, 6t, 1 plus t squared dt. So what do you guys think about this now? Now, I think this probably needs a little bit more. Sometimes people in calculus go, wait a minute, isn't there more going on there? There is, because remember, this is going to be really in purple there. If you want to look at it that way, this is really 6t squared square root, which is the absolute value of 6t, which would be 6t over this interval because the interval goes from t values from 0 to 1. That's my t value. So that's a positive value. So just to let you guys know, that's where the 6t comes from, you know, for that radical. But now, how do you guys integrate this? What do you guys use? Use what? U sub. So remember how we started this whole course and I said to you guys, go back and review U sub, do some U sub. I sent you videos, U sub. I wasn't joking. U sub didn't go away, did it? Never went away. So du dt is 2t, or dt becomes du over 2t. 0 to 1, 6t, square root of u, and then that's du over what? 2t. T's goes away, so this is going to be 3 integral 0 to 1 u to the 1/2 du. So we get 3 u to the 3/2, okay, over 3/2. And this is no longer t. So now this is going to be u, okay? So this is t is 0. This is t is 1. What is u? Well, when t is 0, u becomes 1. And then when t is 1, looks like u becomes 2. So we're going back using this here. Okay, using your u sub. This is proper u sub. Convert your limits as well. So this is now 3 times 2/3 u to the 3/2. U is 1 to u is 2, which is going to be, you have canceling the 3. Tu, u to the 1/2. Do your simplification for u to the 3/2 right in here. Right? I taught those Calculus 1 students how to do that. U to the 3/2 is really u to the first power times u to the 1/2. And you say, well, why is that? Because you're going to have 2 times 2 square root of 2 minus 2 times 1 square root of 1. You'll have 4 square root of 2 minus 2, or factor out the 2 and you get 2 square root of 2 minus 1. Either would be your answer. So, ladies and gentlemen, as you guys can see, you know, be very careful with some of these, though. You want to be careful because some of the integrals are going to be easy. Some are going to use some identities from like trig. And then some integrals, like for example, you might have to use a formula here. Now on tests, in-class tests, I never give questions where you have to use a formula like that. But I got to be careful with what I say because you say, well, that's not true, and you're right. But here's what I'm getting at. Okay, I'm going to give you guys a little heads up here. This question here you're going to see behaves very similarly, but you got to use a formula. Okay, so this is, we're going to find some arc length for some of these here. We're going to go to Desmos. We're going to try to see what does that look like in Desmos, right? So in Desmos, again, you might say, what is my x formula? That's t now divided by 1 plus t. Okay, and then you have natural log 1 plus t. Put natural log. 1 plus that t value. Okay, and that'll be 0 to 2, I think, right? And you guys know I do not like that red. Okay. So double check. So take a look. As you guys can see, it's not like these curves are very sophisticated. Is that right? Even though they are in a sense, but you know, you're trying to find the arc length of something like this from 0 to 2, right? So it's not that it's that sophisticated. If it was a sophisticated curve, you'd have to use a numerical method like Simpson's rule because you won't be able to integrate. So you use numerical methods. But anyway, okay. So now you might say, well, why do I have to be careful? Well, all right. If you have to find x prime again for the arc length formula, yes, that's dx dt. We're using quotient rule. And so by quotient rule, you're going to get what? 1 plus t squared squared, 1 plus t times the derivative of the numerator minus t times the derivative of the denominator. And so you say that's 1 plus t minus t over that 1 plus t squared, which gives you simply 1 over 1 plus t in parentheses squared there. So that's your dx dt. That's your x prime. Are we okay with that? You guys got that for the derivative? Looks like we're okay, right? Now, y prime, you differentiate the y, which is natural log 1 plus t. Okay, so remember that's 1 over 1 plus t by chain rule, the derivative of 1 plus t, and that's 1. So you end up with y prime being 1 over 1 plus t. So there's your y prime and your x prime. So you might say, do I need x prime squared plus that y prime squared? And yes, do I got to take the square root? You certainly do. So you got the square root and you got your x prime squared, which will be 1 over 1 plus t squared, that whole thing squared, plus 1 over 1 plus t, this thing squared. Do some algebra. 1 over 1 plus t to the 4th plus 1 over 1 plus t squared, and you're taking the square root there. So now you might say, how in the world am I ever going to supposed to do what? Integrate this, right? Well, you're going to have to do some simplification here. You're going to have to use some algebra again. Okay, so what does the algebra say? Well, what's under the radical, you got to have the same denominator, right? So let me double check here. Yeah, you got to have the same denominator. So this is going to be, if I multiply the top by 1 plus t squared and the bottom by 1 plus t squared, I'll get that 1 plus t to the 4th here. Still, now you got the same denominator. You got 1 plus t squared over 1 plus t to the 4th square root, and you take the square root of the numerator, 1 plus t squared over the square root of the denominator, 1 plus t to the what? 4th. So I still have 1 plus t squared, and that's going to reduce me to 1 plus t, everything to the second power here. So you guys know there. Now, you might say, I have to integrate this. I think this is from 0 to what? Was that 0 to, what was that, 0 to? I think it's 0 to what? 2 dt. So if you look at this now, you might say, what in the world is this? How do I integrate this? Well, what do you guys do again, right? What do you use? You use u sub. Where now u is going to be 1 plus t. Excuse me, which means du is dt. U. So write your integral. This is all in terms of t, right? This is t equals 0, t equals 2. So here's my arc length now. If t is 0, u is 1. If t is 2, u is 3. Take the square root of 1 plus u squared. Everything over what? U squared, and then that's going to be du. Okay? Now here is my point to you. Here, up in here, you might say, how do I integrate this? Well, what are your tools to integrate? Right? How would you integrate this? I would say probably use what? Use trig sub. So this is where it goes back to, you know, how you do some of these kind of questions here. You're going to use trig sub here. And after you do that, to let you know, even in the book though, they do have a nice formula. And sometimes in the solutions, they'll say, hey, use the nice formula. If you ever look at that, and, you know, but you can use trig sub, use the nice formula here, where that formula in your book is going to be minus square root u squared plus 1 over u plus natural log absolute value u plus square root u squared plus 1. So if I evaluate that from 1 to 3 for u, you get minus square root of 10 over 3 natural log 3 plus square root of 10, okay, plus that square root of 2 minus the natural log of 1 plus the square root of 2. So using u sub or using that formula in the book, you're going to get, you know, a nice answer like this. But notice the interesting thing. This is kind of, what should I say? This is a little bit sophisticated for, in terms of values of, you know, in terms of a number. And that corresponds to just a very simple what curve there, as you guys can see. Generally speaking, like I've always told you guys, you can't find the exact arc length. This is why some questions in the book say set it up only. So sometimes I want you guys to know, they'll tell you, just set up the integral. Don't even do it. The reason they say just set up is because you really can't integrate. Okay, so I just want you guys to know on homework to note they will only ask you to set up some of these because you can't integrate. And then in some, they should ask like some Simpson's rule, you know, versions. Use Simpson's rule, you know. And that's kind of how I see, you know, some of those kind of questions in my mind. Looking at this arc length here. Okay, and so now let's take a look at some of you say, what about the area questions I shared with you guys? What about area, right? You go, okay, you shared with us some area. And they're going to maybe say, if I look at your book, let me see if I find one. Okay, let's do this here. All right, that tells me. All right, so let's do an area here, and it's really bounded area. So it looks like they want to give you bounded area. So let's go through that, okay? So we're going to look at area, but it's really bounded area. So they'll say find the area bounded by the curve. X equals cosine t, y equals e to the t. So here's your curve. It's parametric though. This thing, and what else they do? And they'll say, and the lines y equals 1 and x equals 0. So this is kind of a bounded area question. Okay, So here's your area question. It's a bounded area question. Let's kind of look at some details. Let's go to Desmos here. I'm going to look at some of these details here. So, okay, parametric curve. What is that curve? X is cosine t. So we're going to say cosine of t. And we're going to scroll out, comma, cosine t e to the t. And 0 to pi over 2, I think, right? Was it pi over 2? Yeah. Okay. All right. Now, x equals 0. And y, is it y equals 1? So let's do this here. Let me change some of the colors here. Let's do it all blue. Okay. So I'm going to do this. I'm going to say to you guys, let's try to see if I can get that picture in Desmos. So I'm going to import that in Desmos. Okay, Notability, add to existing note. Where is it? Your calculus of parametric equations here. No, not that one. I think it's this one, yeah. Okay. There we go. So you might say, what are they asking us to do? Do you guys remember Calculus 1? Bounded area questions? How are bounded area questions, right? We're looking at this here. Okay, you guys okay with that? Now, how do the bounded area questions work? So area is going to be, do you guys remember, isn't it the top curve minus the bottom curve? So if I wrote this from Calculus 1, this approximating rectangle, right? You guys remember that approximating rectangle? This is always from Calculus 1. This is area from the top minus area from the bottom, which is going to be two integrals. Y top minus y bottom. Is that true? Dx. Okay, you guys okay with that? So far, it's just Calculus 1. The bottom curve is y equals, what is that? Bottom curve. Y equals 1. This is that horizontal line right here. So y is 1. I want to share with you guys. There's that bottom curve. Okay? So y is 1 on the bottom there. X is 0 is another way of saying this is your y-axis. That's why you have that anyway. So what does that mean? What's the y on the top curve? The y on the top curve is right here. This is the orange. Okay? Does that kind of look okay to you? So that my area is going to be e to the t minus 1. And yeah, that's dx. So far, so good? E to the t minus 1. So there's the y's there. What you're seeing is in orange and blue. Okay. Now, what is dx? You say we have to have that dx. So you got to convert your dx. Sorry, wrong color. We'll use gray. So dx, you say, here's my x. X is cosine t. So that means then dx dt. What's the derivative of cosine? Minus sine. So what does that mean about my dx then? So that means my dx will be minus sine t dt. So I replace this with minus sine t, what? dt. So now, ladies and gentlemen, we're going to now have this e to the t minus 1 times the minus sine t dt. This is your area formula, which is now going to be 1 minus e to the t sine t dt. Or let me keep it that way. Okay. So I'm going to keep it this way. This is minus e to the t minus t. Don't forget that minus sine t dt. Now, what's the issue here? This is x is 0 to pi over 2. These are my... Is it x is 0 to pi over 2? No, 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 no. T. So let's be careful. This was x really from what? 0 to 1. Okay? Oops, let me do this here. Yeah, see if you guys... Let me highlight it. Wasn't that interval from 0 to 1? But what do we have to be careful about? Do you guys remember? Remember when I gave you guys the area formula here? Where's that area formula? In my formula sheet. No, not right there, right here. Remember this area formula here? You got to care about the orientation. So we got to find the initial point and the terminal point. Which situation is it? Is it the first situation or is it the second situation? Right? I got to find my initial point and my terminal point. Because t goes, where does t go from 0 to what? T goes from 0 to... T goes from 0 to pi over 2. So this is always the case. Always give it to you as increasing t. So the question is, do I write 0 to pi over 2? Right? Is that 0 to pi over 2? Or is it going to be pi over 2 to 0? What do you have to do? Do you guys remember? Go back and look at the orientation here. Where's my first point here? So if I plug in 0 here for t, right? Where's my initial point now? X, what's cosine 0? 1. So that means x is 1. What's y going to be? What's e to the 0? 1, 1, 1. So here is, ladies and gentlemen, the initial point. Okay? Now, let's let t now be pi over 2 here. Let's find the terminal point. Pi over 2, pi over 2. What's your x coordinate? What's cosine of pi over 2? Cosine 90 degrees is what? Your x value now is what? 0. Your y value is e to the pi over 2. So you say, where is that? That's right up here. So here's my terminal point, ladies and gentlemen. What am I trying to say to you guys? What's your orientation now? Your x coordinate is what? Decreasing. It's getting smaller. So your dx dt is in fact negative. Now, why is that a big deal? What did we say in our formula? What does that formula become? All of this, right? Remember, your t is going to be between alpha and beta. So if you want to write your t that way, right? Alpha less or equal to t, less or equal to beta, what do you actually have to have? You put a what? The negative sign in front. So you can be consistent with your alpha being what it is. You know, because otherwise you're going to have to write it how? That way, backwards. Otherwise you write it backwards. Remember, alpha is less than or equal to beta. This is how we always describe our t. Smaller to larger. The left is on the smaller, the right. So, okay, let's go back to our work now. Where's our work? Where is it? Here. So if you want 0 to pi over 2, here's my point. If you write it this way, what do you have to do? Put a negative. And how does that help you? That's now minus a minus, which is plus. So this is now going to be 0 to pi over 2 e to the t minus 1 sine t dt. This will be your area. Okay. Oops. And how would you guys integrate this? You guys know? What do you guys use to integrate? Integration by what? Parts, IBP. So all those little tools do not go away. You know, the things that we've done in integration, U sub doesn't go away. Integration by parts does not go away. And I could give you guys this area here so you guys know it's going to be 1/2 e to the pi over 2 minus 1, I believe, at the end of the day. Now, what do you guys want to also note here? How do you know when you might have done this wrong? You see this area? Your area needs to be positive. Area under that curve is positive there. The bounded region is a positive area. You know, it goes back to calculus 1 that the top area minus the bottom area, that's going to be a net area that's positive. So if you get a negative area, you might have forgotten about the orientation of the curve. So this is kind of like a bounded area question. You can forget about orientation. And you don't want to forget about orientation. I don't know if I can find what this curve is really, and even if I did, you may not be able to integrate it. I think I can. If you guys want to know, you say, Mr. Judge, what curve is this? But don't do this. Right? Don't do this. I mean, I understand if you want to. This is natural log of y being t. So then your x is really cosine of what? No, let's do this way. Don't do it that way. No, forget about it. Don't even go there. Don't even go there. Just keep it as parametric equations, because if you try to convert it and integrate, you're going to have a problem. And like I said before, not everything is you know, it can it be integrable, you know? And even if we look at another one, let's see, kind of like that. Bounded area. Yeah, this is kind of an interesting one. I don't know if we have time. I don't know if we have time for this one, another bounded area question, right? I'm going to say bounded area. X is t minus 1 over t. And then what is your y? T plus 1 over t. Okay, that's kind of a thing there. And they want the line y equals 2.5. Okay. So let's kind of see if we can do some stuff in Desmos here. T minus 1 over that t comma t plus now 1 divided by t. And then you now have the line y equals 2.5. And let's see if there's more information here. Okay. They should have more information. And the line 2.5. Okay. I think they should have some more information. T, let's go. T goes from 1 to 50. There we. Okay, now I see what they did. You guys see what they did? They didn't have any restriction on that T. Okay, you guys see what I mean? That T is not restricted. It's weird. So what do you think they're talking about for bounded area? Do you guys see what I'm saying? Yeah, they're talking about your area here. Is that right? This is what they're talking about. So I'm going to try to get this in here. Because they didn't restrict your T anywhere. But this is what they're saying here. Okay. So import that into Notability. Add to existing note. I think we're in, there we go, here. So is that right? Okay, you guys okay with that? Now, how would you start to do this? Because we're out of time. How would you guys start to do this? Approximating rectangle, right? So they want you to find this whole area. So my area is, again, y top minus y bottom dx. Where the top area, you guys know this is going to be something, did we screw up on that? Yeah, we did. It's 2.5. There we go. Apologize. Not 25, but what? 2.5. Okay. So let me see if I can, yeah, there we go. That's better, sort of. If we actually make our, we can change this to what? Your y-axis can be your x-axis. Let's make that smaller. Let's say from -1 to +1, maybe. It's kind of like that, I guess. Okay, that's your picture. It's not 25. I thought something's really wrong. All right, so it's a lot nicer. Import that into Notability. Get rid of this one. This is not right. Delete. Cut. Uh-oh. Where's our picture? It's a nicer one. So yeah, we're going to take to add to existing note. And it was, which one is that? I think it's the top one. Yeah. Here we go. So you want to go back to Calculus 1 and remember a few things here. How are you going to deduce this here? It's going to be, yes, this is going to be 2.5, by the way. Okay? And the bottom curve, what's your y value? It's right here. So that's minus the, whatever that y is, what is that, t plus 1 over t? So t plus 1 over t. Okay. And you're going to need to get dx, by the way, dt, but you're also going to need to find what? These values. And you want to find the orientation. So I'll let you guys go and think about that because we're out of time. But anyway, ladies and gentlemen, that's another one in your book. Don't forget to get your dx, though. You say, what is our dx, right? Isn't this 1 minus what? Isn't that 1 plus, what is that, t to the minus 1? Is that 1 over 1 plus t squared? 1 over t squared. Okay, dt. So I don't know. Double check, ladies and gentlemen, because you need that x prime. Is that right? Is that true? Yeah. 1 plus 1 over t squared. So I want you guys to do that, and then double check your orientation on how you integrate that. You want to do it in terms of t. All right. So anyway, we're out of time. Take care. We'll see you guys tomorrow. We'll continue with surface area as well as surface area tomorrow. So we'll see you guys later. First, in case you guys were wondering, so take a look at that. I put that all in the chat, and I'll try to figure out when I get home some fixing of that website, because I do know it's a weird thing. People don't, it's a very technical thing that, whatever, I won't go through that detail. Okay, but we're going to do some surface area questions, but I want to kind of remark about that bounded area question we were looking at yesterday. Remember that bounded area? And of course, bounded area answers are always positive. But you might say, Mr. Judge, what are the limits on this? They didn't even give us some limits. How do we get the limits? Right? Because it's a strict bounded area. And how do you really get the limits? Well, do you guys remember this. If you look at the endpoints, yes, there's some symmetry, so maybe we can use that, but okay. Do you guys remember from Calculus 1? What do you guys remember? Both curves, right, share the same x and y coordinate values. Is that true? Do you guys remember that, both curves? And now, though, this is parameterized. So you need a value t here, and it turns out you need a value t over here. There's two values of t because we need some limits. And you say, what is my, you can say, you know, there's a t here, a t value, and a t value. Maybe t1, maybe t2, I don't know. And then you have to consider the orientation. So you need t. We have all the other stuff here. And then you're going to say, well, how do I get t? Because you're going to do some algebra there. So the boundary area. So do you guys know, anybody have an idea? How do you get that t value? Right? Well, go back. Yeah, go back over here. See your two y equations? One's a horizontal line and the other's not. Okay, you guys okay with that? So what do you do to get t, is what I'm saying. What is t now? Well, here's what t is, right? You set the two, since these have share the same y value. So you say you set y equal to y. They're the same. So now you can say t plus 1 over t better be, it's really 5 halves. Is that true? 2.5? Is that 5 halves? And then you get to solve for t. Now, you're going to get a quadratic. Right? You say, how do you know we're going to get a quadratic? Because this becomes t squared over t plus 1 over t is 5 halves, I believe. Is that true? Yeah, t over t, so you can multiply that here. And you can multiply both sides now by the LCM of 2t. So you might say, well, what does that do? Well, I mean, you can do a couple things. T squared plus 1 over t is 5 halves. And let's do this. Let's solve this here because we're going to try to find the t values. Two t squared plus 2 equals what? 5t, cross multiplication. And then 2t squared minus 5t plus 2 equals 0. Now, hopefully, if you're lucky, you can factor. If not, what do you guys use? How do you solve for t? Double check. Double check to see if my algebra is okay. Okay, double check. I think that's good. 2t squared plus 2 is 5t. And okay. So how do you guys, is it factorable? I hope it is. If it's not, did they make this thing factorable? I hope. Is it factorable? 2, 1. Is that true? Let me double check. 4t. Is it factorable? It might be. Are we good with that? Let's double check. 2t squared for the first term. The last term is plus 2. What about the 09? Minus 4t, minus 1t. Is that minus 5t? Looks like it's factorable. I'm happy when it's factorable. You get 2t minus 1 is 0. T is 1/2. T minus 2 is 0. T is 2. So double check my work, okay? Is that right? You guys good with that? Did I make a mistake? I hope not. I think we're good. Okay. So you might say, well, what does this mean? Right? Looks like you got two values of t. T is 1/2 and t is 2. So what does that mean? Let's find out here. Let's do the easier one. Well, let's find out. What happens when t is 1/2? Okay, we're saying we have the x and y value, or the y values are the same when t is 1/2 and when t is 2. Has the same y values. So if I go back, let's find out this location. Let's plug in what? 1/2 for t. Is that true? So what happens now if we do that? What's your x value? Is that 1/2? Yes, that's 1 over 1/2. Isn't that 1/2 minus 2? And then what does that be? What's 1/2 minus 2? Is that negative 3/2? Double check. Is that true? So x is negative 3/2. So where is that x being negative 3/2? Ah, this is when t is what? 1/2. You know, I'm going to go back here. This is that point. So this is where x is negative 3/2. Okay, you guys okay with that? And I didn't get the y value, but I already have the y value. It's right here. Y is 3/2. It's 2.5 because it's the same y value as above. And now you go, okay, what about the other x value, Mr. Judge? Okay, what's the other, I'm sorry, the other t. What's the other t? Is that 2? So you go, okay, what's x now when t is 2 now, right? So now you go, okay, x will be 2 minus 1/2, and that means x is going to be a positive 3/2. Okay, you guys go with that? So that x value is where now? Right? So, oops. This happens when t is what? 2. So your orientation looks like this. Is that right? Because that's where, you know, this is where x is 3/2. And you can kind of double check because it's over here somewhere, right? These x values. Negative 3/2. This is where x is positive 3/2. This is where x is negative 3/2 on the curve. So the orientation does have your dx, dt. In other words, isn't your x coordinate value increasing? Okay, x is increasing. And maybe I should use the black color because your x value when t is 1/2, your x value over here, right? That's the x value. That's the x value. So x is increasing. Now that's good because you say, well, what does that mean? That just means I replace these values with what? This would be t is 1/2, and this would be t is 2. So these are t values now. Okay, so this is t. I want to make sure you guys are aware. So I'm just kind of going through again, how do you get those t to finish off this bounded area questions? It looks like they only have bounded area. Now, don't forget, you had to convert this dx, right? So even though, if I go back, let's erase this here. This dx dt is 1 plus what? T squared, which means that dx will be 1 plus 1 over that t squared dt. That's the dx that we just put here yesterday. So now everything is in terms of t. Is that true? Right? Everything's in terms of your t now. So let me do some of this. You go, okay, well, what does that mean there? Well, our area, the integral, t is 1/2 to 2. And you got this here. 5 halves? So you got this 5 halves minus what? T plus 1 over t. And then that's going to be multiplied by that 1 plus 1 over t squared here. Okay? dt. And, so then you can say, okay, I got that bounded area to be 1/2 to 2. 5 halves minus, maybe you want to write that as t squared plus 1 over t. And then maybe this is also going to be a what? T squared plus 1 over t squared, I guess. dt. Let me double check the algebra. Is that right? And double check here. Okay, let's see what kind of the algebra you get now here. So this portion here, 2t, this would be 5t minus 2 t squared plus 1 over 2t. And you have that t squared plus 1 over that t squared. 5t minus 2t squared minus 2, it looks like, over 2t. T squared plus 1 over that t squared. So you're going to start to do the algebra right up in here. That's what I mean. So, okay, let's do that really quick. This is 5t cubed, first terms, minus 2t to the 4th, minus 2t squared, okay, plus 5t minus 2t squared minus 2t cubed. And then hopefully there's going to be some terms that we can combine. So it looks like we get, let me write it in descending order, okay, minus 2t to the 4th, double check, plus 5t cubed minus 4t squared plus 5t minus 2 over 2t cubed now. So let's distribute that t cubed, okay? In fact, yeah, let's do that there. Let's only distribute the t. So this would be 2, negative 2t, plus 5, minus 4. There's going to be a t there, and I'm going to factor out the 2. Okay? I'm focusing just on that t now, plus 5 over t squared, it looks like, minus 1 over t cubed. So just double check that algebra so that I can actually pull out the constant in the integral. T goes from 1/2 to 2, negative 2t plus 5 minus 4 over t, 5 over t squared, and that's a minus 1 over t cubed dt. Okay, so I just want to leave you guys. I was just going to have you guys get started with that. And now you can actually integrate this not too bad. Okay, so this is integrable. but that'll give you the bounded area. And your area should be positive, by the way, right? You say, how do we know that area is positive? Because it's a bounded area question there, right? That's a positive area there. So I just want to share with you guys a bounded area we started yesterday, because some people might have a little more detailed, say, how do I finish that? So now we've seen a couple of those, but let me go to the notes here again and remind you guys, we're going to try to look at those statistics. You're going to look at the surface area questions. It's all the way down here. We did arc length, some bounded area, and that leaves us now with surface area, right? So I'll go through the notes on the iPad if we have that. I think we do. Oops. It's in the notes. Where are you? That's not it. I got to find it. Yeah, okay. So I'm looking on my iPad, and I'm going to transition here. So let's go through that. Yeah, okay, let's go through that. Okay. So remember the idea last time, right? You start with that formula, surface area, integral 2 pi r ds, and you have to determine r, you have to determine ds. So let's see if we remember some things here now, okay? Now, your S is right here, which means the ds, there's only one ds formula. So there's not two. So this is your ds formula. So if you notice what we did last time, right? The surface area, when you rotated first about what? Remember you rotate about the what? We did this. This portion is the ds, right? Oops, let me see if I can be very careful. There's my ds. There's my ds. And see if you guys remember. Remember when you rotated about the x-axis, wasn't your radius the y-coordinate value? Do you guys remember that in our notes? We looked at that and you go, oh yeah, the radius is always y. So that's why here, to say to you, in the surface area formula, your r is what? Y. So this is what you're going to use if you rotate about the x-axis for a parametric curve. Okay, you okay with that? It's kind of easy peasy. It's easier. There's only one ds, not two. And you go, well, okay, what if we rotate about the y-axis? And I don't know, maybe we'll use a different color, I'll do orange. R is y. R is y. Now, what if you rotate about the what here instead? The y-axis. What was r then? Radius. X. Isn't this your ds? Okay, you guys good with that one? So, and you say, well, where am I getting my x and y? Well, my x, remember, this is parametric, so x will be some f of t, y is some g of t. Those are given to you. And then, of course, t is in an interval, whatever that is. And here, this is alpha less than or equal to t, less than or equal to beta here. And then remember, do you care about orientation when it comes to arc length? So when it comes to arc length, this is where it's different. You don't care about the orientation. You don't care if it's x is increasing or x is decreasing. It's not like the area question where you care about that. The only time you care about orientation is for area, bounded area. Surface area, different. You say, why? Because for ds, remember the ds didn't matter. Orientation doesn't make a difference when it comes to arc length. That length. That means x could be increasing or decreasing. Part of the proof I gave you guys in your book talks about it, but it doesn't prove it like I did. That's why I created the notes. So in other words, this is a very simple kind of process. You just worry about this. All right, so now let's look at an example here. And let me try to find some. All right, what is this here? Okay, let's go back to this kind of example. Let's see if I can find it. Okay, so I'm going to take this curve x equals 2t cubed and y equals 3t squared. And we're going to look for t to be 0 to 1. Okay, you're going to rotate about the x-axis. Determine your surface area. And I thought maybe if I have it, I thought I had it in decimals. Well, let's take a look then if I don't have it. X is going to be what? X was 2t cubed. So 2 t cubed. Y is 3 what? T squared. And t is between 0 and 1, right? So we're taking that curve and you're rotating it about the what? X-axis. So I'm going to take all of that in and say, okay, import that into Notability. Not a new note. Calculus of parametric equations. I think this is it right here. I hope. There we go. So just to kind of remind you guys, right? You're taking that, right? And the radius is the y value. So that's why we say radius is y value. When you rotate about the x-axis, right in here, your radius is that y value right here. It's vertical. Okay, you guys okay with that? So that's why when I mentioned to you guys, oh, it's going to be very simple. If you rotate about this x-axis, then your radius is y. Now, why is that important? Because what's your surface area formula? Right? Your surface area formula, again, generally speaking, 2 pi r what? ds. Well, your radius we said was y, so it's 2 pi y what? ds. And then your ds is the square root x prime squared plus y prime squared dt. Where now t is from 0 to 1, because they told you 0 to 1. You didn't have to find that value. But what is y now? Do you guys remember what y is? Y is 3t squared. So you're going to replace your y here with what? That's your y. It's 3t squared. That's what they want you to do. But you really have to find what? This is the ds. You got to find that ds. So, in other words, we're going to have to differentiate the x value, differentiate the y value, square them, and add them, and take the square root. So, what is x prime squared? You guys know? Yeah, x prime is going to be what? Is that 6t squared? Okay. And what's your y prime going to be? 6t. So, square root 6t squared squared plus 6t in parentheses squared. Square root of what? 36t to the 4th. 36t squared here. So your surface area formula really is 0 to 1, 2 pi times 3t squared square root 36t to the 4th plus 36t squared dt. So I want to colorize everything to see your y value and your ds here. So this is what you got to, this is really what you have to integrate. This is an exact value question. They didn't say set up. You got to determine that. All right. Now, you might say, what do we really do here? Well, you're going to have to do some algebra right in here, right? You're going to have to factor out that 36t squared, and you're going to be left with t squared plus 1, it looks like, dt here. And then that's going to be 6t squared 2t plus 1. So your surface area formula, we integrate 0 to 1, 6 pi t squared times 6t square root t squared plus 1 dt. Okay? So it looks like we're going to pull out the 6. This is 36 pi. 0 to 1. Is that t cubed? Square root t squared plus 1 dt. All right, so double check, ladies and gentlemen, that I'm doing the arithmetic okay. It looks like I'm good. But then what do you have to do? You have to integrate. So you have to integrate this. And then you go, oh my God, how in the world do you integrate this one? Well, it's a U sub question again. Yeah, it's U sub. A lot of these, come down to be U sub. So, I mean, remember I said to you guys, I said, you got to work on U sub. You got to work on U sub. U sub. That's why I even started with that video. And you might say, well, what is my U going to be? Well, let's try this out. We're going to let U be what's under here. Okay. And then you say, well, what does this give you? Well, that means du dt is 2t. And then that means dt is du over 2t. 2t cubed, square root of u, du over 2t. So look at the algebra. This is extremely important here. Your t's cancel, and that's a power 2 now. And now you have t squared square root of u. I'm going to pull out that 1/2 here. And this is du. All right, you guys good with that? Be careful, though. Be careful. You cannot integrate this the way you see it, right? Why do I say that? There's two variables. This is t squared and this is square root of u. This is two variables. You can only integrate this if it was one variable, either t or u. Now, since you did u sub, it needs to be u. Okay, you guys with me on this? So you might say, what do I replace my t squared with? How do I handle? Actually, in some of the homework questions in the book here, they actually dealt with some of these kind of things, if you guys noticed. What do I mean by that? Go back up here. If u is t squared plus 1, solve for t squared. What's t squared going to be? Do you guys know what t squared will be? That'll be u minus 1, is that right? So you replace this now with u minus 1. This is still a u sub kind of question. U minus 1, this is now u to the 1/2 du. Your limits have to be in terms of u, though. So you're going to have to convert your limits as well. It's not just t. You got to convert the limits. So remember, this is t now. T goes from 0 to 1. So you go, okay, well, how do I get my u? Well, replace, here, t is 0. That means u is 1. Is that true? So the lower limit is going to be u is 1. The upper limit now, you say t is what? What's 1 squared plus 1? Isn't that 2? All right. So that's going to be u is 2. You got to convert the limits as well. And then algebraically speaking, that integral is going to be 1 to 2. This is u to the 3/2 minus u to the what? 1/2 du. Easy peasy lemon squeezy. Now, you guys can integrate this. Notice this. This factor of 1/2 is here. So I'm going to say 3/2 plus 2. This is 5/2. 1/2 plus 1. Isn't that 3/2? This is over what? 3/2. You evaluate this from 1 to 2. One-fifth u to the 5/2 minus 1/3 u to the 3/2 from 2 to 1. And now I'm gonna share with you guys something here that maybe, oh, what? Well, should we simplify that? You guys know what I mean? Isn't that 2.5? So it's u squared u to the 1/2 minus 1/3 u. That's 1 and 1/2 u to the 1/2. One-fifth 2 squared square root of 2. 1/3 2 square root of 2 minus, well, now u is 1, so it's going to be 1/5 1 squared square root of 1 minus 1/3 1 square root of 1. And now that's 4/5 square root of 2 minus, looks like 2/3 square root of 2 minus 1/5 minus 1/3. And then that portion here, you're going to say you got, well, you're going to have to do some algebra here, right? Some arithmetic. What do I mean? 4/5 minus 2/3 square root of 2 minus 1/5 minus 1/3. So double check, ladies and gentlemen. Is that 12 minus 10 over 15? 3 minus 5 over 15. Okay. So 2/15 square root of 2 minus, which really makes it a plus, because 3 minus 5, isn't that negative 2? That's 2 square root of 15. Double check. But don't forget, what's the deal? Don't forget what? That's just the integral. There's a factor here of what? Is there a 36 pi factor? Constant? So, I mean, you can factor this out. You can say, isn't that 36 pi 2 over 15 square root of 2 plus 1? 72 pi over what? 15 square root of 2 plus 1. And can you simplify that fraction, right? 3 goes into 72 how many times? 24. 3 goes into 15 5 times. Anyway, ladies and gentlemen, there you go. You're done. Here's your surface area. So there's a surface area example. Again, it's just going to be some algebra and U sub. And that's a question where you rotate about what axis? The x-axis. I want to try to rotate about the y-axis for you guys on 1 here. Yeah. So I got some of these. Let me put this back really quick here. Vertical. I got some volume examples, but that has nothing to do with you guys in this class. So let's get some other surface area. Try not to make it try to make it doable in our time span. Let me see. Let me read this. Yeah, surface area. Okay. Oh, y-axis. Okay. Yeah, here's a good example. All right, good. Pulling one from the book. Okay, you're going to determine the surface area. Now they're going to give you x equals e to the t minus t. Well, before e, t over 2, again, t goes from 0 to 1, and now you rotate about, let me double check. Y-axis, yes. Now, again, ladies and gentlemen, I mean, you don't really have to do this, but I think I am. But let me share with you guys this in Desmos. Okay, so your x will be equal to e. No, I apologize. That's not how they do it. They do it differently. E. E to the t. Is that right? E to the t what? Minus t. And then 4e to the t over 2. Okay, it looks like we're good there. Now you can rotate this curve about the y-axis. Okay, you guys see what I'm saying? Yeah. Ooh, what happened? That's odd. Okay, so I'm going to share with you guys this again, this picture. You're rotating about the y-axis, right? And so remember, you're kind of doing the following, and I guess I kind of screwed that up a bit, but that's okay. You'd never guess both my parents are artists. What's the point? What's your radius? X. So doesn't that kind of make sense again? We see that radius is going to be the x value. Is that right? Because in our surface area formula, that's going to be the integral of 2 pi r ds. Now the radius again, right in here, it's going to be now this x value. So replace that with e to the t minus t. Okay? E to the t minus t. There's your radius value. The ds part, though, we got to replace ds with, again, square root x prime squared plus y prime squared dt now. Okay, and then you go, well, what in the world is that? What is my x prime? You guys know, I'm gonna move this out of the way. Okay, rotate about the y-axis. What's your radius then? X. And x is parameterized. So now you get your what? X prime going to be, isn't that e to the t minus 1? Is that true? Is that your derivative, x prime? What's your derivative for y prime? That's 4 e to the t over 2 times 1/2. Chain rule, ladies and gentlemen. Those derivatives, they don't go away. Is that right? Chain rule. My God. Okay. So 4 times 1/2 is 2. So now, square root e to the t minus 1 squared plus 2e to the t over 2 squared. Ladies and gentlemen, this is where our work's going to be, right? So we got square root now. Let's do some work here. E to the t minus 1, e to the t minus 1. Plus, that's going to be 4 et. I'm going to square that one. That one's pretty easy to do. This other one, keep with me, e squared, e to the t, isn't that e to the 2t? Minus 2e to the t plus 1 plus 4e to the t here. Square root e to the 2t now plus 2e to the t plus 1. Now I'm happy. Why am I happy? Do you guys see the pattern here? You guys know what I'm saying? Let me emphasize this pattern here. This expression is right in here. Okay, e to the t minus 1 to the second power, when you use FOIL, is e to the 2t minus 2et plus 1. But then, what do you end up with? Something similar, but now with a plus sign. The sign changed because you added that factor of 4et. Is that right? The sign changed because right in here, you added that factor. So what do you think that means? You guys know what that means? This is the square root of e to the t plus 1 squared, which is the definition of absolute value, e to the t plus 1. Now your t goes from 0 to 1, which means this absolute value is gone. That's positive there. So what's under the radical is positive. So you got to get rid of the absolute value. It's just e to the t plus 1. So moral of the story now. Surface area, integral. T goes from 0 to 1, 2 pi r, not r, x. What is x? E to the t minus t. We knew that, right? E to the t minus t. But that's multiplied by e to the t plus 1 dt. Okay, let me undo that. Here's that x value, and here is ds. Okay, or your r, if you want to think of it that way. Here's the r, which is x, and there's your ds. So again, you're going to need to integrate. So your surface area is going to be that integral 0 to 1, multiple of 2 pi. We have to do algebra. So FOIL, ladies and gentlemen, that's e to the 2t, outer terms, plus e to the t, inner term, minus t, e to the t, last term, minus t, dt. And then this is where you're going to need to what? Integrate. Now, the only one that might be an issue to integrate, what's the only one? Do you guys know? Right? So I'm gonna say this. Let's focus on this integral. What's your time like? What do you guys notice here? By properties of integration, this is e to the, this is what? Let's use our sum and difference formula. Is that right? what do you think you got to do here? What's that integral? Use what? IBP. What do you use here? U sub. So this integral, isn't that 1/2 e to the t over here? And don't forget, this is just going to be what? Plus e to the t, right? And then it's going to be minus, and this one out here is minus 1/2 t squared. Is that true? So what is IBP? Do you guys have that one memorized? It is, but here's what I'm saying. I want you guys to note this. That some of these integrals you may have memorized. Anybody know what that is? Right? Is this is t e to the t minus what? Is that minus t? Is that what you guys get? I don't know. I don't have it memorized. I'm an old guy. Our memory's bad. Is that the integral? So u is t, dv is et dt, so that means v is et. So, okay, uv minus integral v minus v du? I think you're right. I'll take your word for it. But, you know, us old guys, Jesus. And I never thought I'd be old. I'll tell you guys that. I'm warning you. Don't blink. You'll get old. Bless you. So I'm just, oh yeah, I think we could combine these two terms here. Isn't that going to be, here's what we're going to get. 3/2 e to the t minus t e to the t minus t. And then, oh, I think, is that a minus 1/2 t squared? I think so. Anyway, let's not forget, we're going to have to integrate that from what? 0 to 1. So this is kind of a nice thing. 3/2 e to the 1 minus 1 e to the 1 minus 1 minus 1/2 1 squared minus, now that's 3/2 e to the 0 minus 0 e to the 0 minus 0 minus 1/2 0 squared. And you end up with 3/2 e minus e minus 1 minus 1/2. I think all of that, don't forget, there's a minus 3/2 here, right? Because e to the 0 is 1, so that's a minus 3/2. So double check. And that looks like that's going to be, is that 1/2 e minus 1? Or is that just 1/2 e? I'm not sure. Double check. Did we do everything okay? That's 2t. Something was bothering me. That makes this plus. Okay. So what does that give us? Okay, so this is a little bit different. Let's be careful here. All right. So I always have to go back and double check, being old, but you guys are not, you don't have that problem. All right, let's go take a look, right? So now, if we can simplify that, this is going to be, I don't think we can. This is 1/2 e to the 2t plus e to the t minus t e to the t plus t minus 1/2 t squared. Evaluated that from t is 0 to 1. So we get 1/2 e to the 2 times 1 plus e to the 1 minus 1 e to the 1 plus 1 minus 1 half 1 squared minus 1 half e to the 2 times 0 plus e to the 0 minus 0 times e to the 0 plus 0 minus 1 half times 0 squared. 1 half e squared plus e minus e plus 1 minus 1 half minus what? I think that's minus a 1 half. Is that right? Let's double check. Minus 1 half e to the 0 is 1 plus another one e to the 0. Okay. All right. And then your e's are gone. So it looks like we have 1 half e squared plus 1 half minus 3 halves. Is that true? 1 half e squared minus 1. Is that right? So double check we did not screw it up. Because we need a multiple of 2 pi. Is that right? So multiply this by what? 2 pi. 2 pi over 2e squared minus a 2 pi. And so it looks like we get pi e squared minus 2 pi. I don't know. That pi e squared minus 2. So double check, ladies and gentlemen. That's still a positive number, which is good, but that doesn't mean we're right. So double check my arithmetic, ladies and gentlemen. Make sure this integration by parts, is that what it is? U is t. dv. E to the t. du is dt. v. E to the t dt, which is e to the t. uv minus integral v du. T e to the t minus integral e to the t du is dt. T e to the t minus what? Is that minus e to the t? Ah, there it is. That's the problem right here. That's what was bothering me. Double check. Yep, double check. So here's what's going to happen, ladies and gentlemen. So where are we at now? Okay. That integral was not right. I knew I should have done it. That doesn't look right to me. So remember, this is going to be minus, which is going to make this thing here, when you write it down, 1 half e to the 2t plus e to the t minus t e to the t plus e to the t minus 1 half t squared. So you get 1 half e to the 2t plus 2 e to the t minus t e to the t minus what? 1 half t squared. Evaluate that from t is 0 to t is 1. And I can tell you what I get as a final answer. And you guys could double check this. I'm not sure what that is. Anyway, we'll have you guys double check that one. Should we double check? Should we do it ourselves? We have time? Does t go from 0 to 1? Looks like. Yeah. Well, I'll tell you what I get. I get at the end pi e squared minus, this is 2e minus 6. Here's your final answer. Possibly 1/2 e squared plus 2e, e to the 1, minus an e to the 1, minus 1/2 1 squared, because that t is 1 now. Now t is 0. 1/2 e to the 0 is 1, plus 2e to the 0, that's just 0. 1/2 e squared plus e minus 1/2 minus, is that 5/2? Yes. 1/2 e squared plus e minus 6/2, which is 3. But don't forget, you got a factor of what? 2 pi here. There it is. Factor of 2 pi. So, there we go. So let's distribute, I guess, or let's just distribute the 2. So you got your pi e squared plus 2e minus 6. And yes, sure enough, that is the answer. This is the answer I got prior. So yes, be careful that you're using the right what? Formula. If you have it memorized. That's the moral of the story. The integral of t et dt is actually t et minus et, not minus a t. And there's your final answer. Good to go. So again, there is extra examples there in those videos where I shared with you guys. If you want to see some more of those kind of things in the browser, but let's